This is Unit 10, Lesson 11. We're going to talk about features of exponential and logarithmic graphs today. And you're going to be given a graph and you're going to be asked to identify if the graph is exponential or logarithmic. And they're going to give you the equation along with the graph. So that's going to be pretty easy to tell. It's exponential if you've got an exponent that involves a variable. Exponential equations will have horizontal tangent lines, and horizontal tangent lines are of the form y equals a number. You have to, when you're identifying horizontal or vertical tangent lines, those are not just numbers, those are equations of lines. So if it asks for the horizontal tangent line, the answer would be y equals whatever the number is that horizontal tangent line is equal to. Logarithmic equations will have a log in the equation, and then they will have vertical tangent lines. And a vertical tangent line is of the form x equals a number. And when you identify a vertical tangent line, you do have to have the x equals to be correct. Just writing down a number would not be right. And then we're going to, again, identify the domain and range. That's just a review. And then we're going to talk about where the function is increasing and decreasing. Again, we've talked about that before, but we're putting a bunch of stuff together in this section. And then we're going to talk again about end behavior. Several of these things we've talked about already this year, but we will keep coming back to them because they are important and they're different aspects of graphing that you need to understand and you need to know how to identify. So the first thing that we're going to do is identify whether something is an exponential or a logarithmic equation. And to do that, if you just look at the equation here, this one is exponential. This one is also exponential. You know they're exponential because the exponents involve variables. That's what makes them exponential equations. Exponential equations will have horizontal asymptotes. To identify logarithmic equations, in the logarithmic equations, they will either have a log, log, or a natural log, ln, in the actual equation. So they're pretty easy to identify when you're given the equation. And logarithmic equations will have vertical asymptotes. In this section, I'm going to review increasing and decreasing. And you might recall that earlier in the year, we talked about when a function is increasing and decreasing. A function is increasing if, as we move from the left to the right along the graph, it's going in an upward direction. And we're talking about x values going from negative infinity to positive infinity. So this function is increasing as x goes from negative infinity until x gets to -3. Then it starts in a downward position at -3 until we get to -1. So this function is decreasing from -3 to -1 for those x values. Then it starts to increase again as we go from -1 to 2. As x goes from -1 to 2, it's increasing. The function then decreases again as it goes from 2 to 4. It decreases. And then this function increases again as x goes from 4 to infinity. So to do a quick review about how to write increasing and decreasing intervals, remember we use set notation to do that. And we're talking about the x values of the function. So as x goes from negative infinity until it gets to -3, it is increasing. It's increasing again from -1 to 2, and it's increasing again from 4 to infinity. And these again are x values. We're using parentheses because it does not include any of those numbers. It's not increasing at -3 or at -1 or at 4. It changes from increasing to decreasing at those spots. It's neither increasing or decreasing. It's actually at a zero slope there. So we would say that this function has parentheses from negative infinity to -3 because neither of those are included. You always use parentheses for an infinity symbol. We're using parentheses from -1 to 2 and again from 4 to infinity. None of those endpoints are included in the interval where it's increasing or decreasing. So it's decreasing from -3 until we get to -1, and we're talking about the x values again, from 2 to 4. Again, we use parentheses because those endpoints are not being included. In this slide, I want to talk about the same image, but this time we're going to talk about the end behavior. To do end behavior, what we do, or what we're looking at, is this arrow right here and this arrow right here. So for this arrow, this is moving in a left direction and a downward direction. When we're talking about what's happening with the x is approaching negative infinity. So as x moves left, what is y doing? Well, y is going down, so it's approaching negative infinity. And if we look at this arrow, it's as x approaches the right, y is approaching, it's going in an upward direction, so it's approaching positive infinity. That's how we identify end behavior. As x moves left, y moves down. As x moves right, y moves up, is what this means. Another thing we've talked about before is domain and range. A domain is a list of the x values, or what values are included as we move from left to right. The range is a list of the y values, or what values are included as we move up and down. So what we're going to do is we're going to look at this graph. Notice this side of the graph continues in the leftward direction forever. It's just very gradual. This one, it moves to the right direction forever, just very gradual. So since this one's moving forever toward the left and forever toward the right, our domain will be all real numbers. So if you want to use set symbols for that, you could say the domain goes from negative infinity to infinity. It doesn't matter which way you do that. Whichever way they allow you to do it in Delta Math is what you would use. I think usually they're going to want you to use set notation like this. We use parentheses, again, anytime we're using an infinity symbol, because we can't go, it can never include infinity. It goes forever. We never know where that ends. Range is talking about up and down. So if we start at the bottom and move our way up, this graph doesn't start until we get to this position right here, which is -4. So the range starts at -4 and then goes up forever from there. So my range will be from -4 to infinity. This is how I would write my range using set notation. Because it includes -4, I use a bracket. But then, since it goes to infinity, we end that set notation with a parenthesis. Another way I could write that range is, so the range goes from -4 to infinity. It's the -4 is included. The infinity goes forever. So we don't need that to be less than or equal to. So for this one, we're going to find all three things. We're going to determine the domain and range, determine the intervals where the function is increasing and decreasing, and then find the end behavior. So this function, the domain, it goes toward the left forever, it goes toward the right forever. So the domain is going to be all real numbers, and all real numbers is written as negative infinity to infinity. The range, it never goes past 0. 0 is the asymptote. This one is an exponential equation because it goes up forever very quickly. It's increasing exponentially. So it starts down here at 0. 0 is our asymptote, so it never crosses 0, it never touches 0. So 0 is not included in the range, but it does go up forever. So my range for this one would be from 0 to infinity. And it would look like this in set notation. So our range goes from 0 to infinity. If we're determining the intervals where the function is increasing and decreasing, well, if you look at this, as we move from the left to the right, this function is increasing across its entire domain. So it's never going to be decreasing because it never changes direction. As we move from left to right, this function is getting larger. So this function is increasing on its entire domain. And I believe when we get to these type of problems, they're just going to ask you, because we're only going to be dealing with exponential and logarithmic functions, and they're going to ask you if the function is increasing or decreasing, because it will only be one or the other if you're dealing with exponential or logarithmic functions. And then to find the end behavior, this function goes as x approaches negative infinity, it approaches 0. So for our end behavior, we would say as x approaches negative infinity, in other words, as x moves left, y approaches 0. It's asymptote. And then for the second part, for the right-hand side, as x approaches infinity, y also approaches infinity for our end behavior on the right. So when you're dealing with an exponential equation and it has a horizontal asymptote, as you move, it could be left or right, but one of them is going to approach the asymptote at y, for the y. Now we're going to find the same things for this equation, and this is a logarithmic equation. The shape of it is logarithmic. It's got a vertical asymptote here at x equals 0. For the domain and range, if you look at this, the domain starts at 0 and goes forever. So for my domain, it does not include 0, but it does go to infinity. For my range, it goes down forever. So it starts at negative infinity and goes up. And it looks like this does continue forever in that gradual direction. So it goes to infinity in the upward position as well. So my range goes from negative infinity to infinity. Determine the intervals where the function is increasing and decreasing. Well, if you look at this, it starts at the bottom and is increasing over its entire domain. So this function is increasing, and we could say it's increasing on its entire domain, but for the examples that we're going to be doing, it will either be increasing or decreasing. It won't be doing both. So this one is said to be increasing. And for the end behavior, on the left side and on the right side, this end behavior is a little bit different. X is not going to approach negative infinity. Normally with end behavior, we say as x approaches negative infinity, but this time it's never going to go past 0. So we would say as x approaches 0, y approaches negative infinity. And as x approaches infinity, y approaches infinity. It goes up infinitely. It's a gradual increase, but it does go up infinitely. So now I'm going to switch over to Delta Math, and we're going to do a couple examples in Delta Math so that you can see how these work. This one is an exponential equation. You can see here by the equation that they've got drawn that it's exponential because you have a variable in the exponent. So down here it says the function f of x is, and it gives you a choice, exponential or logarithmic. We're going to say exponential. The function with and does this have a vertical or a horizontal asymptote? Well, if you look at this, it looks to me like it approaches here as a horizontal asymptote, and it looks like that asymptote is at 6. So it has a horizontal asymptote, and the equation of that horizontal asymptote is y equals 6, because that's where the horizontal asymptote lies. The range of the function, remember range is up and down, the range of the function begins at negative infinity and goes until we get to 6. So it goes from negative infinity until we get to 6, and it does not include 6, that's why we're using parentheses. And it is, well, as you move from left to right, that function is gradually going down, so it is decreasing. The domain of the function, well, it goes forever in the left direction and it goes forever in the right direction, so that is all real numbers, which would be from negative infinity to infinity. And then for the end behavior, okay, the end behavior on the left side, well, the left as x approaches negative infinity, so we can write that down. As x approaches negative infinity, what is y doing? Well, y is approaching that asymptote, 6. So y is approaching 6. And the end behavior on the right side, this side right here, as y, or as x approaches infinity, y is continuing to go down, so y is approaching negative infinity. I would submit my answer, say yes, and we got it right. Now let's do one with logarithmic function. So this one, we can tell by the equation, is a logarithmic function. So the function f of x is, we'll say logarithmic. It is a function with is this asymptote horizontal or vertical? Well, if you look at this side, it continues to go gradually down but this side looks like it's going to go vertical. So it looks like we have a vertical asymptote, and it looks like that vertical asymptote is at -3. So it is a vertical asymptote. Vertical lines are x equals, and this vertical asymptote is at -3. The range of the function, remember range is up and down. Well, this range goes in a downward position forever and in an upward position forever. So it looks like the range of this function is all real numbers, so -infinity to infinity. And is it increasing or decreasing? As we move from the left to the right, it looks like this is gradually decreasing. So this function is decreasing on the entire domain. And its domain is, well, the domain, remember domain goes from left to right. Our domain is not going to pass -3, so it will start at -3 and it will go forever if you look at the direction it's headed. So it's -3 to infinity. The end behavior on the left side, okay, look at the left side. The x value is approaching -3 and the y value is approaching infinity. So x is approaching -3 from the right and y is approaching positive infinity. And the end behavior on the right hand side, as x approaches infinity, as it goes on forever, as x approaches infinity, y is approaching -infinity. It's gradually getting lower and lower. I'm going to submit my answer, and we got that right. So you just have to consider all of those different avenues of what the equation looks like. They're going to give you choices. You don't have to come up with all of them by yourself. Just think about what they're asking you to find and carefully fill in each blank.